Hey yo, welcome to Astronaut. So today is our second video about optics, and today we're focusing on convex and concave lenses. So let's get started.
Feel like an astronaut in what you know about rolling down in the deep.
In physics, there are two principal ways to describe a lens. Convex, which we also refer to as converging lenses, and concave, which we also refer to as diverging lenses. So let's start with convex lenses. We can draw a horizontal axis going through the center of the lens. This axis will help us keep track of everything from here on out. When light traveling parallel to this axis enters a convex lens, it will be refracted towards a point on the other side of the lens. Every beam of light that enters the lens in the same way will be refracted towards that same point. We call this point the focus. The same effect occurs if the light enters from the other side of the lens. It will converge at a focal point on the opposite side of the lens. The distance between the lens and these 2 points is called the focal length. The focal length is the same on both sides of the lens. Now, if I place an object on one side of the lens, we can look at how the light coming off of this object will pass through the lens. I'll start by putting the object at a distance twice the focal length. Let's draw a light ray parallel to the axis coming off the object. As it passes through the lens, the light will bend towards the focal point. We can draw another line coming from the tip of the object through the focal point on the same side of the lens. When this ray hits the lens, it will bend to be parallel with the axis. We can draw another line from the bottom of the object that passes directly through the center of the lens. There are, of course, a lot of other light rays bouncing off the object, but these three allow us to determine the location and boundaries of the image. Our image forms between the intersections of the lines we drew. In this case, the image is real and inverted. What makes an image real and inverted? Well, the inverted part is easy enough to see. An image that is facing down, which we indicate by drawing an arrow, is inverted. A real image is one that forms on the opposite side of the lens as the object. Real images always form below the horizontal axis, and so they are always inverted. The alternative to a real image is a virtual image. You can expect it to have all the opposite properties of a real image, but before I go on listing those properties down, let me show you what a virtual image looks like. This time, let's move the object closer to the lens, halfway in between the lens and the focus itself. Again, we can draw a line parallel to the axis and let it converge to the focus on the other side of the lens. Now, since we are in front of our other focus, we can't actually draw a line passing through this focus. However, we can imagine a line stemming from the focus. Once it hits the lens, it will bend to be parallel with the axis. Clearly, these lines are not going to converge on the right-hand side of the lens. However, they will converge on the left-hand side of the lens. The resulting image is upright and virtual. It is virtual because it is a projection of the rays rather than being a direct result of the rays themselves. Virtual images always form above the horizontal axis and are thus always upright. Alright, one more scenario. What will happen if the object is placed on the focus? We can draw a line parallel to the axis that will bend towards the focus. Another line will pass straight through the center of the lens. These two lenses are parallel, meaning they won't converge on either side of the lens. No image forms. Okay, so these three examples illustrate some of the key possibilities for what will happen if I put an object in front of a convex lens. If the object is farther than the focus, a real inverted image will form. If an object is closer than the focus, a virtual upright image will form. If the object is on the focus, no image will form. Remember, convex equals converging because the lines converge together. You can probably guess what will happen in our alternative scenario, concave lenses. But let's draw it out. Concave lenses. If I place an object a little beyond the focus, we can yet again draw a light ray parallel to the axis leading towards the lens. Once it hits the lens, the ray will diverge in a direction that can be traced back to the focus. We can draw another ray passing through the center of the lens. The intersection of these two lines indicates where the image will be. Here, we have an upright, virtual image. If I move the object in closer, between the focus and the lens, a similar situation will occur. I draw my rays, one that starts out parallel to the axis and the other that passes through the center of the lens, and find that yet again, an upright virtual image will form. Diverging lenses always form virtual images. One scenario that we haven't yet discussed is what will happen if we put an object at infinity. Now, I know that sounds a little bit strange for a physical representation, something on Earth, right? How can you have an object at infinity? What does that mean? Imagine just a really long distance, right? For a convex lens, all the light rays will converge towards the focus. A real image of no height will form at the focus. For a concave lens, all the light will diverge away from the focus. A virtual image of no height will form. We've discussed a lot of different scenarios without even throwing in numbers into the mix, so I want to take a moment to summarize everything we've discussed. We have two main types of lenses: convex converging lenses and concave diverging lenses. If I place an object beyond the focus of a convex lens, a real inverted image will form. If I place the object between the focus and the lens, an upright virtual image will form. For both cases with a concave lens, an upright virtual image will form. If the object is placed at the focus, no image will form. If an object is placed at infinity, an image will form at the focus. For a convex lens, the image will be real. For a concave lens, the image will be virtual. In our next video on optics, we'll talk about the thin lens equation and magnification, which is all about quantifying the distances and heights of the object and image. So thanks for watching this video, and I hope to see you next time.